of a different type. But let's not get into that. The point is you can raise indices on the alpha like this, and in so doing, you can actually define an inner product. You can define an inner product on p-forms. At this point, by the way, I've left R4 for greener pastures. We're just talking about an arbitrary metric at the moment. But you can. How would you take the wedge product of of alpha with alpha? Well, let's say alpha with beta. They're both p-forms. What you do is you contract them. One across. You do this. And you can work it out. This actually defines an inner product on the p-forms. You remember how at the start of our discussion about abstract linear algebra, we learned that you can take I guess I didn't do that. Curses. Lost my words. I'm going to have to, dang it. Well, how about this? We will come back to that at the very end, all right? There's a way in which I can define the Hodge dual arising from this inner product in kind of a surprising way. So it's not just this ad hoc, you just, do whatever's not there. But what I wanted to spend the bulk of the rest of our time on was the problem of translating Maxwell's equations into differential form. So, do you know Maxwell's equations, Travis? Oh, right. I'm sorry. I'm an idiot. So, from that, but not. You're not electrical. You're mechanical. Is that right? Yeah. Okay. I'm putting the wrong kind of engineering on you. But surely other people here are interested in Maxwell's equations. No? Okay, at least one. That's good. Cooper's interested in absentia, right? So I guess we should write down Maxwell's equations, eh? So Maxwell's equations are these. The divergence of the electric field is equal to the charge density divided by epsilon naught. The divergence of the magnetic field is equal to 0. The curl of the electric field is minus partial b partial t. And the curl of the magnetic field is mu naught J, where J is the current density, plus, stink. I've forgotten my dimensional factors. Do you remember? All right, tell you what I'm going to do to keep myself out of trouble, although this is kind of bad, I'm going to set mu naught and epsilon naught both to 1. So this will just be charge density. This will be just, what?
Mu naught times quantity J plus epsilon naught partial E partial T.
Right, okay. So we got that. Great. Now, I will warn you, my notes, there's some dimensional problem in them. In terms of like the dimensional constants, the permittivity and permeability of free space, currently there's something missing in the notes. But generally speaking, so, all right, so here's the interesting thing, getting to the point. We can translate these into four-dimensional differential forms formulation. So that's on our tx, which I'd call space-time, but you know, it seems like it's time-space. So, right. Although I've been watching Naruto lately, and I feel happy about that. So, okay. So one of the things, a couple different things. So in R4, the question is, what do differential forms look like in R4, right? So let's deal with that to start with. What kind of forms do we have in R4 with coordinates t, x, y, z? So by the way, this means that we're putting the speed of light equal to 1 if you're a student of these things. So of course we have functions, right? Zero forms, f, okay. You got one forms. What do your one forms look like? I say alpha. They would look like some function, let's say alpha naught dt, right? Plus alpha 1 dx plus alpha 2 dy plus alpha 3 dz. So if you use your imagination, you can see what we really have here is alpha naught dt. And if you're willing to keep using my notation, this is plus the work form of some vector field, right? But the devil's in the details here. This vector field is not a vector field on R3. It's a vector field on R4 in the sense that its functions are, it has component functions which are functions of space and time. But it is nevertheless something dx plus something dy plus something dz. So you could still write it like the work. We could extend the work form correspondence here. Two forms are a little bit more interesting. Something like beta. Well, now we've got things like, if you think about it, I'll just get straight to the point. Stink. I guess I'll use numbers. Beta 0, 1 dt wedge dx, right, plus beta 0, 2 dt wedge dy, plus beta 0, 3 dt wedge dz, plus beta 1, 2, well, let me say beta 2, 3 dy wedge dz, plus beta 3, 1 dz wedge dx, plus beta 2, 3 dy wedge dz. Now I think you might realize why I did that. So my typical 2 form can be written something like dt, right, wedged with the work form of some vector field. Oh, yeah. Thank you. Thank you. So that, of course, that is a flux form of some other vector field G. So in other words, each 2 form in R4 uniquely corresponds to 2 vector fields, 2 3-dimensional vector fields, 2 spatial vector fields. Not spatial, but spatial. Sorry, I'm an idiot. 3 forms, what do 3 forms look like? Yeah, gamma is something like, and I'll just use A, B, C, D. A, dx, wedge, dy, wedge, dz, plus B, dt, wedge, dx, wedge, dy, plus C, dt, wedge, dy, wedge. This is in no particular order. plus d dt wedge, ooh, bad notation. What do I got? xy, I got yz, missing my zx, I suppose. Anyway, so there's your 3 form. It's not especially exciting. And you guys know there's only one 4 form. It's a constant time. It's a function times dx, dt wedge dx wedge dy wedge dz. All right. So there's some fundamental identities here, which I want to work out by hand with you before I get my projector back out again here. And we can work this out together. It's not a lot of trouble. What happens if you take the exterior derivative of like that dt wedge omega f thing? How's that going to work if you think about it? It's going to give you dt wedge omega f, right? For one thing. What else is it going to give you? That's it for this term. Oh, was that a dt? That was dt, wasn't it? I've lost a d. Oopsie, oopsie. Yeah, so d dt is just 0. That's no bueno. And so we get minus dt wedge d omega f, right? And then plus d phi g. Now you got to be careful. See, because these exterior derivatives, how do they work? D involves partial t, partial x, partial y, and partial z now. So this part stays the same as it was before, but the dt piece is new, right? So this would look something like minus dt wedge. But the thing is, I mean, yeah, there's a, if I rewrite that as a dx plus b dy plus c dz, if I expand on that, you know, what happens? If you think about this, the time derivative part of these total differentials doesn't matter because it's got a dt which it wedges with. So it's only the spatial derivatives that matter here. And so we just get minus dt wedge the flux form of the curl of f. For the same reasons as before. And this piece over here is what? It's two things, right? It's the divergence of g, dx wedge dy wedge dz, just like it was before. But now, also, you've got the, goodness gracious. I don't know how to do this without expanding it. So like partial a, partial t, dt, plus partial b, partial, curses. I can't do that. It's dt wedge what? What goes with a? dy wedge dz, right? And then partial b, partial t, dt. What goes with b? Wedge dz wedge dx plus partial c, partial t dt, wedge dx wedge dy, using ABC for the components of the flux form. Now, if you look at that, you can see what's going on. This is actually nothing more than the flux form of what? Pull the dt, like factor the dt out, right? And look what you've got. You've got partial a, partial t, partial b, partial t, partial c, partial t appearing in the appropriate slots for the flux form. So what you're looking at here is dt wedge the flux form of what? The flux form of partial g, partial t. So we can extend the vector calculus that we did before with forms to 4 dimensions like this. Does that make sense? I mean, I know. And a similar calculation should show what for the, how about like a 1 form? What's d alpha mean? Alpha naught dt, right? Plus omega f. How's that going to work? So this, in principle, it's partial alpha naught partial t dt, right? Plus the work form corresponding to the 3-dimensional gradient of the alpha naught function, right? That's what the exterior derivative of a function is. It's a partial derivative term plus the usual gradient term in 3 dimensions. But that's wedged with dt, right? So this piece, and then plus d omega f. We already know what happens with this. We worked it out. Did we work it out? Worked it out here. But this time I don't get to ignore the dt term. So I think this works out to the work form of the gradient of the 0th component wedge dt. And then that would be plus dt wedge the work form of partial f partial t, if you think about it, and then plus the flux form of the curl of f. So there's what the exterior derivative of a 1 form. It picks up time derivative pieces, but it's still got the curl that we had from before as well. So what that means is that the exterior derivative of a 1 form and 2 form in 4 dimensions, it picks up all these ingredients we need to build Maxwell's equations. Let's not talk about that. That problem, I need to get back to work on it. So, I'll just get straight to the point. We can define this thing called the Faraday tensor. And what is done here is you use the electric field and the magnetic field together to construct a 2 form. And so the 2 form is built from the you have the the electric field wedged with dt plus the flux form of the magnetic field. If you look at the components as a matrix, it looks like this. So it's antisymmetric, which means it's got zeros, and then you got your electric field, and you got your magnetic field. You got people walking on the roof, as usual. Some comments that don't matter to us at the moment. By the way, here's the Hodge duality. Here's how Hodge duality works out in the Minkowski space with the metric I was using over there and I erased. Like Hodge dual, here's Hodge dual in Minkowski space. There's extra minuses that appear because of the weird metric, and it's complicated to explain where they come from and where they don't come from, and I don't think it's particularly interesting to this course, so I'm not going to get into it, okay? But anyway, that's the Hodge duality. If you can define Hodge duality on the basis wedge products, then it extends to the rest of it. By the way, Hodge duality is not nice. Like Hodge duality of a wedge is not the wedge of the Hodge duals. There's no nice properties for Hodge duality. Don't go looking for them. Just warning you. But there are some things. So the Hodge dual of the Faraday tensor, when you work it out according to those rules I just did, what happens is you get this. So the Hodge dual of the Faraday tensor gives you the flux form of the electric field and a work form of the magnetic field wedged with dt. So essentially the Hodge duality in R4, it trades electric and magnetic fields somehow. Very, very interesting. It's not quite that. It's E goes to minus B and B goes to E. So it's not quite just a trade-off, but it's similar. See, because we had E without pluses, without minuses here, and with minuses over there, but the pattern for these are the same as the B's was. Getting to the point, there's also a 4 current that I have to define. So the 4 current is a 3 form. It has 2 things. It has charge density. This rho is charge per unit volume. And this phi is the flux of the charge per, it's the flux of the current density, which is the current per unit area time. But you put those 2 things together, you've got a 1 form, oh, excuse me, 3 form. And, I'm sorry, J is a 1 form. You Hodge dual to get a 3 form. And if you differentiate this thing, work it out, what you end up with is the time derivative of the charge density plus the divergence of the current density has to be 0 if that's 0. That means that if this is 0, that gives you conservation of charge. It says whatever's diverging in terms of the current, it's amounting to the corresponding change in the charge which is there. This is local conservation of charge if you set it equal to 0. And, oh, so I calculated it not once but twice because, I don't know. I'll talk about forms some other day. I mean, potential forms. Here it is, here it is. In all of its stupid glory. You work out the details, and there's probably better ways to do. I think we basically just worked out this detail. We just calculated the exterior derivative of a 2 form over here. So if you just use what I did over here and apply it to the Faraday tensor, you'll get the same thing. What I didn't do was notice that I could pull my dt terms together. See that? These 2 things can be put together, as I did here. And that's especially interesting because you get this wedge dt plus the divergence of B is all equal to df. So see, setting df equals to 0 does what? If we put df equal to 0, we get that 0 and we get that 0. That's half of Maxwell's equations in terms of one differential form equation. And this is automatically true if f is equal to the exterior derivative of something else. That's the next chapter in this story, is that you can write f as an exact form in terms of the 4 potential. The 4 potential is a 1 form. And then the Hodge dual of f gives you equations for the curl of the magnetic field and the divergence of the electric field. These 2, have to involve the current and the charge density. So this, the exterior derivative of the Hodge dual being mu naught times the Hodge dual of the 4 current, that corresponds to, this is called Amperes Law with Maxwell's correction. This guy is where radio waves come from. And this over here, of course, is Gauss's law. But you notice it's suspiciously missing the divided by epsilon naught, which is symptomatic of the larger dimensional problem with my notes. Anyway. So I think I showed you this before, Sam, but since we're here and doing this, we might as well. There's also something called a co-derivative. I'll give you a homework problem on that. It's fun. Co-derivatives take p to p plus 1 forms. You can play games with the Hodge dual to make it go the other direction. Because if you think about it, if you take a form, Hodge dual it, exterior differentiate it, you go down 1, right? Then if you Hodge dual again, you've gone up 1. If that hurt your brain a little bit, I'm sorry. Come on, coordinate change. We'll get to coordinate change eventually. So this example, I thought it would be fun, and we'll stop here today, I guess, to try to understand what would electrostatics look like in 5 dimensions. Suppose you had 4 spatial dimensions and 1 time dimension. How would you study electricity and magnetism there? See, if you set up electricity and magnetism as we have here, there's a natural way to extend it, actually. And so this would be the Faraday tensor in a 4-dimensional, 1-time dimension space. You'd have an electric field, which is still corresponding to a vector field, but the magnetic thing now has 6 components. It's what you might call a flux. It's not a vector field anymore. There's an asymmetry between the number of electric and magnetic components in the electromagnetic field tensor. But anyway, what I do here is just look at, I want to look at the Coulomb field due to a point charge at the origin in 4 dimensions. And so to do that, I just look at this thing we calculated the volume of earlier in the other PDF. And there's my generalized hyperspherical coordinates. R was sigma earlier, you know. We've worked out that the volume of this was pi squared r to the 4th over 2, 2 different ways today. Hooray. The area of S3, the surface volume, I guess, would be, differentiate this. You get 4 over 2 is 2 pi squared r to the cubed. Like, that's still true. I don't know if you've noticed derivative of pi r squared is 2 pi r? Tori, did you ever notice this? The interplay between area and circumference of a circle. Same for volume of a sphere. The derivative of 4/3 pi r cubed is 4 pi r squared, which is the surface area of a sphere. This continues to be true in higher dimensions. So like the surface volume, I really should say, is that. This is really the 4 volume. But anyway, so this would be the charge density of a smeared out charge at the close to the origin in 4 dimensions. And if I assume Maxwell's equations naturally generalized, that would give me the derivative of E wedge dt is equal to 1 over epsilon naught rho this. And so then doing that integral amounts to, by the generalized Stokes theorem, that's the derivative of the boundary of M of that. But since E is symmetric, it's got the same nature. There's no direction. There's no sense of direction. It's a point charge. It's spherically symmetric. So I can just take the surface volume times the magnitude, and that would be this integral, which is 2 pi squared r cubed E is equal to Q over epsilon naught. And there you go. This is Coulomb's law in 4 spatial dimensions. It would look like this: Q over 2 pi squared epsilon naught r cubed, as compared to your usual Q over 4 pi epsilon naught r squared. If you have 4 spatial dimensions, the electric field would weaken faster because it would have another dimension to spread out in. Yeah. Anyway, it's fun to look at. But this is, you know, one of the things, if you think harder about differential forms, you can build models and things that you might not think you ever could have. I mean, it's a tool that you can use to really take your imagination places that, I don't know, I think are fun. I'm sorry, I've gone long enough for today. I'll shut up. You can hit it.